All right, today we're going to be headed back in our packet to some application questions, our quadratic function applications. Most of the time with this, we're going to be finding our min-max values, right, aka vertex, to maybe hopefully minimize costs or maximize revenue. We're going to also be looking at some functions that explain the general movement of a basketball or a volleyball perhaps. And we're going to be doing these algebraically. Also, whenever you see this in your calculator, you can certainly do it in the graphing calculator, but I'm going to be showing you guys through Desmos. A, because it's going to be a lot easier for you guys to use and apply, and B, because I know that not all of us have our graphing calculators handy on us. So remember, these min and max values, they may be found from the y value of the vertex. Right, we're thinking our smiley face, y value, minimum, or our frowny face, hey, that's our maximum value. You can find it algebraically by using this negative b over 2a, and then you're also going to be able to use Desmos through this activity. The first one, I'm going to show you both methods in both ways because you're going to be asked to use both. And then the next one we'll use, next two actually, we're going to use our Desmos to do this. So we want to figure out the maximum revenue. This is our daily revenue function. It's achieved by selling X pairs of shoes, and it's modeled by the equation Rx. So we know X is our number of shoes, right? Number of pairs of shoes. And R, or our Y value, is our amount of money. And really an amount of revenue measured in money. Dollars and cents. All right, so we want to figure out the maximum revenue. When I'm looking at this function, I see that this isn't necessarily in standard form. The A value is this negative 0.01, and my B value is this positive 50. No C value is listed, so my C is 0. So because my A value is negative, right, that makes it being a frowny face, which means I'm going to have a maximum value. So to figure out the maximum revenue here, I'm going to find my axis of symmetry. I'm going to plug that in to find my Y value, and that will be the maximum revenue. So I'll use my negative b over 2a to find my axis of symmetry. So negative 50 over 2 times negative 0.01, which simplifies to 2,500, which you could probably use in your calculator, but just not a graphing calculator, right? So my x value of this function, of my vertex, is 2,500. My x value talks about the number of shoes, right? Pairs of shoes. So when I sell 2,500 pairs of shoes, let's see what that revenue will be. So I'll plug in that x value of 2,500 into my function. And of course, use my lovely handy-dandy graphing my calculator to simplify this. Remember, with PEMDAS, we want to simplify the exponents first, and then we'll deal with the multiplication. So do 2,500 to the second power, and then multiply by that -1. When you do that, you should get 625,000. That is my maximum revenue. So that will go on this line, 625,000 at, and how many pairs of shoes must the firm sell to maximize revenue when you sell 2,500 pairs of shoes? We're remembering to use units on this, so dollars for revenue and then pairs of shoes for that 2,500. All right, we're now going to use the Desmos technology to find our that vertex. So in this function, we're given the marginal cost, C in dollars, of manufacturing X cell phones in thousands, is given by the function c of x, 5x to the second power minus 200x plus 4,000. So the first thing that I'm looking at here is the a value. So I know my a value is positive. That being said, I have this smiley face parabola, which means I will have that minimum value. So when it asks how many cell phones should be manufactured to minimize the marginal cost, right, I will have that minimum value. So I'm finding that y value of the vertex. So that being said, I'm going to go to Desmos.com and hit graphing. And I made my screen a little bit bigger so we could see all of this. So I'm going to type in my function y equals 5x to the second power minus 200x and then plus 4,000. Okay, so I can see absolutely nothing on this graph, which means I'm going to need to do some zooming. So I'm going to zoom out because I also know that I'm going to be trying to hit this 4,000 as that y-intercept. Trying to find that smiley face. I'm going to keep zooming out. Oh, there we go. Now I see this. And then I could zoom in so I can see a little bit closer about what this function looks like, right? There we go. So here is my parabola. I'm able to see this general shape, this U-shaped, and then I'm able to find this minimum value. To find the minimum value, all I do is I click on where it looks like that minimum is. And there's my vertex, 20, 2000. So I will bring that over to my handy dandy worksheet. My vertex, 20, 2000. X represents the cell phones in thousands. And Y represents the marginal cost. And we're talking about dollars here. So how many cell phones must be manufactured to minimize the marginal cost? Cell phones, that's talking about the X, and that's 20. But it's also labeled in thousands. So I have 20,000 cell phones. The minimum marginal cost is this Y value, a total of $2,000. All right, let's try another one on this back side, and we're going to incorporate all of our key features. Okay, this question is about the path of a shot put. So the path of the ball thrown by an athlete in a track and field competition can be modeled by that quadratic function, where D is the horizontal distance in meters and H is the height in meters. So we're going to start to visualize this. We know that our x-axis is really going to be our horizontal distance. Of D, and our y-axis is going to be the height, or that big H, right? Our input goes on the x-axis, our output goes on the y. The horizontal distance is written in what? Meters? Just something to think about, and height is also in meters. Something to jot down. All right, so let's go ahead and take that function and go into Desmos.com and go ahead and type that in. So h of d is equal to negative 0.04 d raised to the second power plus 0.84 d plus 2. And it should go back to that standard graph, that window. So all you need to do is do a little zoom out so you can see the parabola, right, that basic shape of it, and that general right location of it. So I'm just going to sketch this out back on the notes just so I have an idea of what we're describing. So we have that height axis, we have our horizontal distance axis. The y-intercept starts right above, right, that origin. So it's at 2, so I might as well place it at 2. and then we have that general increase, and then we have it decreasing, and then crossing that x-axis, right? So go ahead and compare my graph with that one. Not perfect, but right, close enough to generally see what's going on. Let's go ahead and see what our question is, how we're going to be interpreting it. So what is the maximum height of the ball? Okay, maximum height means what is that max distance that reaches. We can find that by finding the vertex. At what x value, at what horizontal distance, right, will that ball be versus what height will it be? So we want to find the y value of that vertex. We can find that by going to our graph, right, and just clicking on where it looks like it's the maximum, and actually that vertex will pop up and it'll be calculated for us. So 10.5 and then 6.41. With all of these, we're going to round to 2 decimal places, just as a general thing, right, if we don't have that rounded value. So maximum height of the ball is going to be 6.41 meters. How far away, horizontal distance, is the ball from the athlete when it reaches the max height? So when that max height is 6.41 meters, it's going to have a horizontal distance of 10.5 meters. I think this is a really nice way to visualize, right, the path of that shot put right after the athlete releases it at that intersection point. All right, what is the height of the ball when it leaves the athlete's hand, right? So that athlete is right on that horizontal distance versus height axis, right, which is right at the origin. And the height of that ball when that athlete releases it is going to be at that y-intercept. We know the y-intercept is written as 0, c, and in this case, our function, our c value is that 2, right? So this is going to be the y-intercept, which is 0, c. We know 0, 2 is that y-intercept. So the height of the ball when it leaves the athlete's hand is 2 meters. The total distance, horizontal distance, right, when it hits the ground, and the ball hits the ground, right? So this is the path of the ball. It's in the air, it's at the maximum height, it continues up, and then it hits the ground, right? This horizontal axis is the ground. How far did it travel from the person, right, if we're going to jot that person out, right, from the person to where that ball lands? We can find that by finding the x-intercepts. So going back to our Desmos, right, if we were to look again, find the path of the ball reaching the maximum and then hitting that y-intercept, we'll have that y-intercept of 0.16 meters as that x-intercept. So horizontal distance, x-intercept, and it's going to be 23.1, technically 59, but we're going to round it to 2 decimal places, 0.16 meters. So there's some applications, and I think that this will be helpful, especially Desmos, as you attempt some problems dealing with applications on your own.